Hi, welcome back. So let's now look at the practice questions for test 2. So these are the practice questions / problems for test number 2. Okay, let me just make sure. Good. Okay, it's working. Practice questions for test number 2. Number 1. So you have the sheet of practice questions, and so we're looking at that. Number 1 says, if capital X is the maximum of the numerical outcomes of 2 rolls of a die, and capital Y is the number of tails in one coin toss, what is the joint probability density function of X and Y? Okay, so number 1, if X is the maximum of the numerical outcomes of 2 rolls of a die, and Y is the number of tails in one coin toss, what is the joint probability density function of X and Y? Okay, so to do this, we need to know the PDFs of both X and Y, the PDF for X and the PDF for Y. So let's start with the PDF for X, f of X. That's a probability capital X is equal to some fixed value little x. Okay, the maximum of the numerical outcomes of 2 rolls of a die. Right? So if you roll a die twice, right? You roll a die 2 times. For each time, the value on the die could be 1 through 6. Right? So each time you roll the die, you get numbers between 1 to 6. The maximum could be as low as 1 if both rolls are 1, or the maximum could be as large as 6 because one of the rolls is a 6. So the possible values of X are 1, 2, 3, 4, 5, or 6. Right? The maximum value of the 2 rolls could be 1, 2, 3, 4, 5, or 6. And so we would not want to know the probability that if X is 1, 2, 3, 4, 5, or 6. Right? How many rolls are there? There's 36 different rolls of 2 rolls of a die. 6 for the first roll, 6 for the second roll, 6 times 6, 36 ways to roll both dice. So how many ways could the maximum be 1? Well, the only way a max could be 1 if both were 1. So that'd be 1 out of 36. 1 over 36 is the probability the max is 1. Now the probability max is 2. Well, how many ways could that happen? You could have a 1, then a 2. You could have a 2 and then a 1, or you could have a 2 and then a 2. There's 3 ways the maximum is a 2. So that's 3 over the total 36. How many ways could the maximum be 3? You could have a 1 and then a 3. You could have a 2 and then a 3. You could have a 3 and then a 3. You could have a 3 and then a 1. You could have a 3 and then a 2. There's 5 ways the maximum could be a 3. That's 5 over 36. 5 over 36. Right? The maximum, how many ways could the maximum be a 4? You could have a 1 and a 4. You could have a 2 and a 4. You could have a 3 and a 4. You could have a 4 and a 4. You could have a 4 and a 3, 4 and a 2, or 4 and a 1. There's 7. There's 7 ways the max could be a 4. How many ways could the max be a 5? Well, you have a 1 then a 5, a 2 then a 5, a 3 then a 5, 4 then a 5, 5 then a 5, 5 then a 4, 5 then a 3, 5 then a 2, or 5 then a 1. Right, so those are the 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are 9 out of the 36 ways. 9 over 36, the probability the max is a 5. And what's the probability the max is a 6? Well, you could have a 1 then a 6, a 2 then a 6, a 3 then a 6, a 4 then a 6, a 5 then a 6, a 6 then a 6, a 6 then a 5, a 6 then a 4, a 6 then a 3, a 6 then a 2, a 6 then a 1. And so that's 3, 6, 9, 11. That's 11 over 36. That's the probability that the max is a 6. And so if you add up these probabilities, it should be 1. So you get 20, 27, 32, 30, you get 36 over 36. Okay, so that is the PDF for capital X, the maximum of the numerical outcomes of 2 rolls of a die. Okay, so that's little f of x. Now, what's little f of y? Y is the number of tails in one coin toss. So little f of y, well, if you have a coin toss, the possible values are heads or tails, right? And y is the number of tails. So the possible values of y are 0 or 1. If you toss a coin 1 time, the possible number of tails you can get is 0 or 1. So f of little y, we want to know its value if little y is 0 and if little y is 1. But what's the probability that when you flip a coin, the number of tails is 0? That's a probability that's getting heads. The probability is 1/2. And the probability that y is 1, you get 1 tail, it's also 1/2. Okay, so that's little f of x and little f of y. Okay, well, let's also point out that x and y, this is the solution, right? Let's point out x and y are independent events. Right, the outcome of either event has no effect on the outcome of the other event, right? It doesn't matter what the maximum of the numerical outcome of 2 rolls of a die are, it has no effect on the number of tails when you flip the coin once. And the number of tails you get in one flip of a coin has no effect over the maximum numerical outcome of 2 rolls of a die. So x and y are independent events. And so what that means, what that means is that that the joint probability density function of x and y, little f of x comma y, that's the joint probability density function of x and y. That's little f of x comma y. That's a way to find. That's equal to f of x times f of y. Okay? Because x and y are independent events. So the goal is to find little f of x comma y. We know it's equal to f of x times f of y because x and y are independent events. Here's f of x, here's f of y, and so let's just multiply them. So I'm going to erase this list, just give myself some room. This is a good way to see the values of little f of x. Okay, so I want to use this space for little f of x comma y. So little f of x comma y is equal to little f of x times little f of y. And what that's going to equal, I'm going to use big brackets again. Well, if x is 1, the probability is 1 over 36. Take 1 over 36 and multiply it by 1/2. You get 1 over 72. So f of x comma y is 1 over 72 if x is equal to 1 and y is equal to 0 or 1, right? Okay, and so all these values are going to be for y equals 0 or 1. It's not going to make a difference whether y is 0 or 1. You're always going to multiply by 1/2. So 3 over 36 times 1/2 is 3 over 72. It's 3 over 72 if x is equal to 2. It's 1/2 times 5 over 36, which is 5 over 72 if x is equal to 3. If x is equal to 4, it's 7 over 36 times 1/2, which is 7 over 72 if x is equal to 4. And then 9 over 36 times 1/2 is 9 over 72 if x is equal to 5. And then 11 over 36 times 1/2 is 11 over 72. If x is equal to 6. Okay, and so this is, all of these are for y equals 0 or 1. You gotta write that there, or you could write y is 0 or 1 next to each one, but that would be a little redundant, but okay, I'll just do it so it's clear what I mean, so that you understand what I'm saying here. Okay. You could write all of these for y equals 0 or 1 there. Okay, and so given a value of x and y, let's say x is 2 and y is 0, then the f of 2 comma 1 would be 3 over 72. Okay. And so that's the joint probability density function of x and y. That's the joint probability density function of x and y, and we found it. And so that is the answer to number 1. Okay, good. Okay, let's keep going. Okay, number 2. Let capital X be a discrete random variable with probability function f of x given by f of 3, which is 1/5, and f of 5, which is, and f of 5, which is 4/5. Find e, the expected value, e of x squared plus 3x plus 9. Okay, so step 1, find e of x. So step 1 for our solution is going to be find e of x. And so e of x is the sum of all possible values of x times f of x. Right? Our x here is a discrete random variable, so its expected value is defined that way. If it's continuous, you'd be using the integral, right? The integral from negative infinity to infinity of x f of x. Okay? Yes. But this is a okay. So the possible values of x are 3 and 5. So this is going to be 3 times f of 3 plus 5 times f of 5. And so what that's equal to is 3 times f of 3, which is 1/5, 3 times 1/5 plus 5 times f of 5, which is 4/5. That's equal to 3/5 plus 20/5, that's 23/5. Okay, so the expected value, e of x, is 23/5. So step 1 is done. Okay, step 2 is going to be find e of x squared. So e of x squared, separate that, e of x squared is the sum of all possible values of x squared f of x. And that's equal to, the possible values of x are again 3 and 5. And so let's write that here, right? X could either be 3 or 5. Okay, so it's 3 squared times f of 3 plus 5 squared times f of 5. 3 squared is 9. 9 times f of 3 is 1/5. Plus 5 squared, which is 25, times f of 5, which is 4/5. So you have 9/5 plus 100/5. That's 109 over 5. Okay, so e of x squared is equal to 109 over 5. Okay, good. Listen, e of x squared plus 3x plus 9 is equal to e of x squared plus 3 times e of x plus 9. And so e of x squared is equal to 109 over 5 plus 3 times e of x, which is 3 times e of x, which is 23 over 5, plus 9. So that's equal to 109 plus 69 over 5. 109 plus 69 is 178. So it's 178 over 5 plus 9. 69 plus 109 is 178, because it's 169 plus 70 minus 1. So it's 109 plus 70 minus 1, which is 179 minus 1, which is 178. So 178 over 5 plus 9. 9 is 45 over 5, and so 45 plus 7, 178 is 223. So it's 223 over 5. That's the answer. 223 over 5. That's the value of e of x squared plus 3x plus 9. It's 223 over 5. All right, and so that's the answer to number 2. Okay, so that's number 2. Okay, so number 3, suppose xy takes on values on the square (0, 2) cross 1, 3. With the joint PDF, f of x comma y is equal to 7/2 x cubed y. Find the marginal PDFs. F sub capital X of x and f sub capital Y of y. That's number 3. Okay, suppose x comma y takes on values on the square 0, 2 cross 1, 3 with joint P of f of x comma y equals 7/2 x cubed y. Find the marginal PDFs f sub x of x and f sub y of y. Okay, so the solution. Okay, so f sub capital X of x, that's equal to, and so this is going to be this is a continuous random variable. So this is the integral from negative infinity to infinity of f of x comma y dy. okay? And we'll do this one first, and then do the next one after. This square, 0, 2 cross 1, 3, if you look at the xy axis here, then that region is in that rectangle there, that square. And that square from x values 0 to 2, y values from 1 to 3. And so if we were going to find f sub x of x, the probability that x is some fixed value, let's say this was x here, say that was x there, we would be integrating over all possible values of y. But the only y values that would be in that square would be the values y from 1 to y equals 3. And so when we integrate from negative infinity to infinity with respect to y, we only need to integrate from 1 to 3. The rest of it doesn't matter. Okay? So this is the integral from y equals 1 to y equals 3 of f of x comma y dy. And that's equal to definite integral from 1 to 3 of f of x comma y, which is 7/2 x cubed y dy. And so that's with respect to y. And so you get x cubed, you get 7/2 x cubed, because that's 7/2 x cubed is a constant. X cubed is also constant because you're integrating with respect to y. That's definitely from 1 to 3 of y dy. And then that's equal to 7/2 x cubed y squared over 2. Evaluate from 1 to 3. And so then that's equal to 7/2 x cubed times y squared over 2 from value from 1 to 3. So that's 3 squared over 2 minus 1 squared over 2. That's equal to 7/2 x cubed times 3 squared over 2 is 9/2 minus 1 squared over 2, which is 1/2. 9/2 minus 1/2 is 8/2, which is 4. That's then 7/2 x cubed times 4. And so 4 divided by 2 is 2, so you get 14x cubed. So f sub x of x is 14x cubed. And so we found this one. Okay, f sub capital X of x is equal to 14x cubed. So now we're going to find the next one, f sub capital Y of y. So f sub capital Y of y is equal to the integral, before this was from the definition. This is also from the definition. And keep in mind, x and y are continuous random variables, which is why it's an integral. This is the integral from negative infinity to infinity of f of x comma y dx. And so with respect to x. And so now if we look at this picture again, but for here, so now I see we have room here. If I have room, we're going to go from x from 0 to 2, y from 1 to 3. That's still the square. But now we're going to fix y, and we're going to integrate over these values of y. Right? If we're integrating with respect to x from negative infinity to infinity, all the x values that will matter are from x equals 0 to 2. And so this will be the integral from 0 to 2 of f of x comma y, which is still 7/2 x cubed y, but dx. Right? So if we fix our y here between 1 and 3, and we integrate over all possible values of x, the only x's that actually matter from 0 to 2. Okay, so we integrate that, and that's a 7 there. So first we take out the constant 7/2 of y. Now y is a constant because we're integrating with respect to x. So this is 7/2 y, definite integral from 0 to 2 of x cubed dx. And so this is equal to 7/2 y times an antiderivative of x cubed, which is x to the 4th over 4, evaluated from 0 to 2, times that. And this is equal to 7/2 y times x to the 4th over 4, which is 2 to the 4th over 4 minus 0 to the 4th over 4. And so that's equal to 7/2 y times 2 to the 4th is 16. 16 divided by 4 is 4. 4 minus 0 to the 4th over 4 is 4 minus 0. And so this is 7/2 y times 4. And so that's a 4. That's y. Okay, 4 over 2 is 2. 2 times 7 is 14, so that's equal to 14y. So f sub capital Y of y is equal to 14y. And we got that there. So now we found f sub capital Y of y there. That's for the integral of 3. Okay, and so we have now solved this problem. I can put a little box here at the end to denote that. So that's number 3. Okay, let's keep going. Okay, so number 4. Number 4 is let capital X be a discrete random variable with cumulative distribution function. Capital F of X below. A, find probably capital X is less or equal to 3, probably X is less or equal to 5, probably 1.5 is less or equal to X, less or equal to 0.2, and then probably X is equal to 10, and probably X is greater than 10.2. Okay, so we're going to find those 5 probabilities, and with the cumulative distribution function capital F of X below. So I'm going to write capital F of X here. So capital F of X is 0 for X less than 2. 0.2 for 2 less equal to X, strictly less than 5. 0.6 for 5 less equal to X less than 10. 0.8 for 10 less equal to X less than 10.5. And 1.0 or 1 for 10 for X greater than equal to 10.5. Okay, so that's the cumulative distribution function capital F of X. So for A, it's find these 5 probabilities. Well, the probability that capital X is less or equal to 3 is equal to capital F of 3. And according to this, capital F of 3 falls in this range, so it's 0.2. P of X less or equal to 5 is the probability X is most 5, which is capital F of 5. And what's capital F of 5? Well, X is 5, not this one here, 5 less or equal to X. This is less than 5. This is including X equals 5. So that's 0.6. Okay, so this one, we did this one. The probability that 1.5 is less than or equal to x less than or equal to 7.2. That's equal to the probability that x is less than or equal to 7.2 minus the probability that x is less than or equal to 1.5. Right? The equals and not equals doesn't make a difference. And so we end up with this. And so then this is equal to, well, this is capital F of 7.2 minus capital F of 1.5. And so capital F of 7.2 falls in this range, so that's 0.6 minus capital F of 1.5. 1.5 is less than 2, so capital F of 1.5 is 0. So 0.6 minus 0 is 0.6. And so that's that probability. The probability that x is equal to 10 is 0 because we have a continuous random variable. Oh, the probability x is we have a discrete random variable. Oops. Right. This is a discrete random variable. So the probability that x is equal to 10. So when x is going up to 10 here, the cumulative probability is 0.6. When x then equals 10, it jumps from 0.6 to 0.8. That means just adding the probability when x is equal to 10 means the cumulative probability goes from 0.6 to 0.8. So that means the probability that x equals 10 has to be 0.2, the amount of jump from here to here. So probably x equal to 10 is 0.2. Okay. Okay. So that's that. Probably x is greater than 10.2. So the probability that x is greater than 10.2 is 1 minus the probability that x is at most 10.2, less than or equal to 10.2. That's 1 minus capital F of 10.2. And what's capital F of 10.2? That falls in this range, so that's 0.8. So it's 1 minus 0.8, which is 0.2. And so probably that x is greater than 10.2 is 0.2. All right, so those are the 5 probabilities there. That's part A. That's part A of number 4. Okay, part B. Part B, so for part B, here's capital F of x, right? The probability x is at most anything less than 2 is 0. When x equals 2, it jumps from 0 to 0.2. So for our little f of x here, the probability that x is equal to 2 is 0.2, the amount of jump from 0 to 0.2. Now, up to 5, before x is 5, it stays 0.2. Then when x equals 5, it jumps from 0.2 to 0.6. That means the probability is 0.4 if x is equal to 5. When x equals 5, you add 0.4 to probability. When x equals 10, you add another 0.2. So it's 0.2 if x is equal to 10. And then when x stays the capital F of x stays 0.8 until x is 10.5. Then it jumps from 0.8 to 1, and so that's 0.2 jump. So it's 0.2 if x is equal to 10.5. And if you add up these probabilities, 0.2 plus 0.4 plus 0.2 plus 0.2, you get 1. Okay, and so that is the probability function of x. That's a little f of x right there. That's part B, that function. It's the PDF of x. Okay, so I boxed the 5 answers for part A and boxed the 1 function for part B. So that's number 4. Okay, let's keep going. Number 5. Suppose that a point x comma y is selected at random from inside the circle with radius 3 and centered with radius 3 and center 0, 0. Find the joint PDF of x and y. Okay, suppose that a point x, y is selected at random from inside the circle with radius 3 and center 0, 0. Find the joint PDF of x and y. So, solution. Let's look at what the circle looks like. So it has center 0, 0. There's the center at 0, 0. And with radius 3. So let's say here's 3. Here's negative 3. There's a 3 in the y-axis. Here's a negative 3 in the y-axis. So the circle is going to connect those 4 points. So I tried to free circle. Okay, so that's a circle with center 0, 0 and radius 3. So we're going to select a point x, y at random from inside that circle. So we want to know the probability of any particular point in that circle. Okay, well, the area of that circle, right? What is the area of the circle? The area of a circle, remember the formula is pi r squared. So that's pi times the radius, which is 3, squared. So this is 9 pi. Pi times 9, which is 9 pi, right? So the area of the circle is 9 pi. And so the joint PDF of x and y, little f of x comma y, is going to be 1 over the area of the circle, which is 9 pi. Okay, so each point is equally likely to be hit in the circle. And so in a sense, you want the probability to add up to 1. And so if the total area is 9 pi, the probability of any one point, it's not the probability of the point, but the PDF of the function is 1 over 9 pi. If you were to sum up the total area of that circle, you would get 1. Well, that's up to it's a tangent to what we're doing here. All right, so the joint PDF of x and y is that. Right here, this is a continuous random variable, right? X, the point where the point x comma y is. I mean, x and y are each continuous random variable. Okay. Let's keep going. So that's number 5. Done with that problem. Let's go over that. Number 6. Number 6, let x be a continuous random variable with PDF f of x is equal to beta e to negative beta x if x is greater than or equal to 0, 0 elsewhere. Problem is find e of x. Find the expected value of x. Good. Okay, so solution. Okay, so first let's remember the exponent, and then what happens for an exponential random variable, and the PDF for an exponential random variable, right? So let's, as a reminder, let's think of I'm going to call it y. Think of an exponential random variable, capital Y, with, as its PDF, with, let me put it this way, with PDF of the form f of y is equal to 1 over theta e to negative x over theta if x is greater or equal to 0, and 0 elsewhere. Okay, so as a reminder, think of an exponential random variable capital Y with PDF of the form f of y is equal to 1 over theta e to the negative x over theta if x is greater or equal to 0, and 0 elsewhere. Okay, now let's call beta equal to 1 over theta. Let's just make beta equal to 1 over theta. Then what is f of y? What would be another way to write f of y then? F of y, if beta was 1 over theta, f of y would be beta e to the negative x, but now beta is 1 over theta, so negative x over theta is negative beta x. If x is greater or equal to 0, and 0 elsewhere still. Right? Beta equals 1 over theta doesn't change 0. Okay, so that's that. So I could write the PDF this way, where beta is 1 over theta, right? So when you have an exponential random variable y with parameter theta, with PDF of that form, right? So theta would be the parameter, right? Now, remember the expected value of an exponential random variable with parameter theta is equal to theta. Okay, so this is a fact that you can remind yourself of. This can be proved if you have an exponential random variable y with parameter theta. You can show that the expected value of y is theta. That's then if y is an exponential random variable with parameter theta, then the expected value of y is theta. Beta is 1 over theta. Right? Okay, so here's f of y. If we expressed it with beta, where beta is 1 over theta, you would get this. But now, the expected value of y in terms of beta, well, if it's theta, theta is equal to 1 over beta. So the expected value of y is 1 over beta. Right? Well, I'm just going to put that in a box with the answer. So this is pretty much the answer. Almost there. Just change the letter x to y. I mean y to x. So the expected y is 1 over beta if you're using beta this way. Make sense? So here, x is a continuous random variable with a PDF of this form. Because the PDF is of this form, we know that x has to be an exponential random variable with parameter theta. Okay? So as a solution, we know x is exponential, is an exponential random variable, because it has a PDF of that form. And so, the expected value of x is going to equal theta, but theta is 1 over beta. And so, the answer is that the expected value of x for that is 1 over beta. Okay? So I feel this is helpful as a study method to show you this kind of a solution, because I'm using the formula that the expected value of y is the parameter theta of your exponential random variable. And so over here, beta is not theta, beta is 1 over theta. Because in order to get it to look like this, beta has to be 1 over theta. And so since the expected e of x is still theta, still the parameter, you have to think of what theta is in terms of beta. Theta is 1 over beta. So e of x is 1 over beta. And so we found e of x. And we're done with this problem. Okay, so that's number 6. Okay. Good. So one more problem in the practice problem list. Okay, number 7. So for number 7, here's the problem. Consider this experiment. Roll a die. If the outcome is a 4, select a number at random from the interval 0, 2. If the outcome is not a 4, if the outcome is not a 4, select a number at random from the interval 2, 3. Let capital X equal the value of the number selected. Okay? So part A, draw a histogram of this random variable. Assuming x is rounded to 1 decimal place. Okay, so draw a histogram of this random variable, assuming capital X is rounded to 1 decimal place. Good. Okay, so let me just read this again. Consider this experiment, roll a die. If the outcome is a 4, select a number at random from the interval 0, 2. If the outcome is not a 4, select a number at random from the interval 2, 3. Okay. So let's draw a histogram, give myself plenty of space. We'll just extend this line all the way to the end here, in case I need it. Okay. So what values could x take? It could either be between 0 and 2, not including 0 or 2, or it could be between 2 and 3, not including 2 or 3. Okay. x is rounded to 1 decimal place. Okay, so it could be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, 1, 0.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2.0, and then between 2 and 3, be 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9. X is rounded to 1 decimal place. So if it's rounded, it could be rounded to 3. It could be like 2.999 rounded to 3.0, and it could be 0.00001, and it could be rounded to 0. So we'll include 0 in this. Okay. So if the outcome is a 4, it's between 0 and 2, right? So when you roll the die, the possible values are 1 to 6. And so the probability of, the likelihood that when you roll the die you get a 4 is 1 out of 6. Okay? So let's put 1/6 here. Okay, so the probability is 1/6. And so if you're looking at a number from 0 to 2, well, okay, so the length is 2 of this interval, right? And so there's a 1/6 chance to roll a 4, but that 1/6 chance has to be somehow distributed over this interval of length 2. And so it's going to be 1/12. The length of the interval is 2, so it's 1/6 times 1 over the length of the interval 2. So 1/6 times 1/2 is 1/12. It's going to be 1/12. I'm just going to put a 1/12 here. Okay, so what will happen is the probability is 1/12, and so we're making a histogram, and so we're just going to be bars here, where the length of the height of each bar is going to be 1/12. It's going to be from 0 So I'm going to say it's rounded down. Okay, so I'm going to add the word down here. It's going to be rounded down to 1 decimal place. So if it's rounded down to 1 decimal place, it's going to be 1/12 likelihood. Okay, it's going to be rounded down. And so that means it's not going to be overlap with 2. I don't want to overlap with 2. So it's going to be rounded down to 1 decimal place. And so from 0 to 1.9, we have a probability of 1/12. Okay, and so now the probability of being rounded down now so now there's a 5/6 chance that you don't roll a 4. And so the length interval is 1. So it's 5/6 times 1 over 1, which is 5/6. And so now we're just going to be looking at a 5/6 chance. Put the 5/6 up here. And so the probability that would be rounded down to 2 would be 5/6. So there would be a bar here, 5/6 to 2. It won't be rounded down to 3. It'll be rounded down to 2.9. And so that will be 5, 6. So drawing a histogram for this random variable, assume x is rounded down to 1 decimal place. It could be rounded down to 0 and have 1/12 chance. It could be rounded down to 2. It could be in this interval rounded down to 2 to nearest decimal place, to 1 decimal place. And it would be 5, 6, right? From 2 to 2.9 would be 5, 6. From 0 to 1.9. And then down would be 1/12. Okay, and so this is the probability histogram for this random variable, assuming x is rounded down to 1 decimal place. Okay, and so that's A. That's the probability histogram. Okay, so I'm going to erase this to make B. So we need 7 part B. So for part B, it says find the probability density function of x. So find the probability density function of x. And so we pretty much are done with that already because we found probability histogram. So little f of x is going to be, well, there's 2 intervals to consider. It's between 0 and 2 and 2 and 3. So if 0 is less than x less than 2, right? You only choose that number if the outcome is a 4 when you roll the die. It's a 1/6 chance again. This is in length 2, so 1/6 times 1/2 is 1/12. And so f of x, the probability that x is between 0 and 2 is 1/12. And then if x is between 2 and 3, well, you only choose one of these numbers if the outcome is not a 4 on the dice roll. And so the probability of it not being a 4 is 5/6, right? 5 out of the 6 rolls are not a 4. And so the probability is 5, 6. The length interval is 1, so 5, 6 times 1 over the length interval, which is 1. 5, 6 times 1 over 1 is 5, 6. And so f of x is 5, 6 if x is between 2 and 3, not including the endpoints. Okay, so the probability x is strictly between 2 and 3 is 5, 6, and the probability x strictly between 0 and 2 is 1/12. Okay, the total probability does it up to 1, even though 5, 6 plus 1/12 is not 1. The length of this interval is 2, and so it would be 2 times 1/12, which is 2/12, or 1/6. 1/6 plus 5, 6. Length interval is 1. 1 times 5, 6 plus 2 times 1/12. You get 5, 6 plus 2/12. 5, 6 plus 1/6 is 1. So the total probability is still 1. Okay, and so that is the probability density function of x. And that's 7b. Okay? And so now we're done with 7b, and we're done with the 7a and b, we're done with 7. Okay, so those are all 7 practice questions for test number 2. Okay. Good. So I'm going to erase this. So just to remind you of some PDFs, or some things, right? So the binomial probability function, right? Remember that is, remember that, right? When you have Bernoulli trials, right? If you have X successes and N Bernoulli trials with the probability of success, Oh, never mind. Don't worry about it. Okay, okay, so don't worry about that. Forget about that. Okay, so then what else do I want to point out? Right, so remember the exponential random variable looks like this. Remember, for an exponential random variable x has PDF of this form. Right? So I just erased that last that thing. Okay. So for an exponential random variable, it looks like that, right? And if you have this PDF, you know it's an exponential random variable. Its expected value is theta. Okay? If you have a uniform random variable, with parameters alpha and beta, where they're different, alpha not equal to beta, then the PDF of that, so it's a uniform random variable x with parameters alpha, beta not being different. F of x is equal to 1 over, so parameters alpha strictly less than beta. They're different and alpha is smaller than beta. Then f of x is equal to 1 over beta minus alpha if alpha is less than x less than beta, and it's 0 elsewhere. Okay? And so that's the PDF for a uniform random variable with parameters alpha less than beta. It's a continuous random variable. That's also a continuous random. Okay, so just reminding you of those PDFs. Okay, so I hope that helped, and good luck.